It really provides a framework for control of alignment. It really works with helping you control the order of assembly. It is designed to make heavy reuse of components and objects. It's really good for being able to allow people to model in context. So you're able to see the relationship your part has with other parts of the assembly in context way instead of just a blind bottom-up approach. It's considered to be more robust. Then if you kind of talked about the bottom-up approach, a positive point there is literally you can get everybody modeling from the very onset of the project. It's good for small assemblies. It's good for standard hardware. So anything that you kind of purchase as a standard component that you don't manufacture inside your company, those components are generally done kind of a bottom-up approach. And so one of the key things that I was hoping that this discussion would kind of lead to was that most large assemblies, while we talk being top-down, is really a mix of both top-down and bottom-up. It would be difficult, I think, to build something like a jet engine and have all of the screws and fasteners and bearings and things like that be done from a totally top-down approach. There is some of that hardware that just naturally comes in from the bottom up. And so a good discussion here would have brought you, could have brought you 7 points or something close to it if you had that kind of a general discussion. The problem number 5, where we started talking about the topology optimization methods, in this case, the continuous. What I was hoping that I would find in this discussion would have been something about the unit cell and how the void is defined inside of the unit cell. If A and B are equal to 0, there's no void. If they're equal to 1, it's a complete void or empty cell. If I saw this kind of discussion, I think I awarded 4 points, or I should have awarded roughly 4 points for that kind of discussion. To get full credit on this, what I was hoping that you would do is say, this is an example of the 2D mathematics. If it were a 3D object that we were working with, then it wouldn't be a rectangular cell, it would be a cuboid, and it would be 1 by 1 by 1, and some general discussion of how this would be in 3D. I'm not sure that more than 1 or 2 people really kind of explained that. I think most people just kind of threw this mathematics back and didn't tie it into a 2D case. They really didn't say for the 2D case, this is what we found. And so I was maybe a little harsh on grading this problem, but I think it's an important thing to reflect on and think about. This unit cell doesn't have to even be rectangular. And there were a few students that kind of picked up on that and said, assuming that we're using a rectangular type cell to do our meshing or our gridding, then this would be how the mathematics would be set up. Getting into problem number 6, and this was where we maybe didn't spend enough time having you work some examples, and that I'm to be blamed for that. I was hoping that this would be kind of simple enough problem that you could reflect on the definition of Bezier curve and work with it. We said that there was a circle that needed to be approximated by a Bezier curve. We told you that the center of the circle was at the origin, 0, 0, and 5. And we said that the starting point was at minus 0.5, 0, and 5, which meant that this endpoint of the arc was at 0.5, 0, and 5. And so you should have worked on setting up this type of a problem where it was 1 t squared t cubed, the MBE matrix, which we've done many times, and I think most people kind of want into that. And then what I was hoping is that you would kind of fill in the points that you knew. And so the first point that you would fill in is the beginning of the arc, which is minus 0.5, 0, and 5, and fill in the ending point, which is 0.5, 0, and 5, and then put in everything else that you knew. Well, you could easily put in 5 and 5 for the z, and what I was hoping that you would remember is that the control mass from the first point to the second point defines the tangency at the beginning of the curve. And so this point up here, where my cursor is, has to be minus 0.5. You don't know what the y value is, but you could have maybe guessed that it was 0.5 because you know that this point right here on the arc is 0.5. And you know that this ending point, so from this point to the last point, control point, has to control the tangency at the end of the arc. And so you could have put in 0.5, and you could have guessed the y value of something like 0.5. And if you had set that up and actually run the equation through, you would have found out that that didn't work, that your arc at x of 0, the circle value would have been 0.375 or something like that. And so the next thing that you would have done is you just have to resolve the y value. And so you would have maybe guessed 0.6. And so if you put 0.6 into this equation, multiply it out, you get this formula right here, 1.8t minus 1.8t squared. You put in 0.5 to find out what the real value is, and you find out that it's 0.45. And so the next thing you can do is maybe guess 0.7 to try and bracket this. And if you put that in, you notice that the y value when t is 0.5 is being halfway along, you can put that in and you find the y value is 0.525. Well, instead of goofing around with that too much, what I would have hoped you would have thought about and done is said, let's just set this whole thing equal to 0.5 and solve for the y value. Well, at t of 0.5, you put that in. When t is 0.5, you want a y value equal to 0.5, and so you get this equation set up, and the answer that you have to chase down for the y value ends up being 0.666 and on. And so going back into here, what it should have been is minus 0.5, 0.6666, and 0.5, 0.6666. And so knowing kind of the properties of Bezier, I was hoping that you could approach that and solve it. I think we only have about 3 or left in class, so I'll try and do this one quickly. This was a surface definition. The description here is kind of the U and V direction. The U being each curve, and the V being across the curves. And so U goes from 0 to 1, and V goes from 0 to 1 direction. And you should have set up an equation that looks something like this: 1 U squared, the MVE, for the U, the point laid in this way, you just literally and MVE transpose for the V curve. And then you write in 1V squared, V cubed, and V to the. And that would have gotten you 20 points. Now, quite a few of you flipped things around and you had V up the front, and you were basically kind of had this crossed up with a MV place and in the wrong order. I easily had V out front and U in the back, but it needed to be a 1 by 5, 5 by 5, 5 by 3. So you needed to go through and kind of make the matrix map match up to get credit. The surface at U of 1, V ends up being this point right here, and so off of the. And then last question is, what is the normal at that point? What you would do is you would take this point minus point to get a curve, to get a tangent vector in the U direction. You would go this point to get a curve, to get a tangent in the V direction. And so that's what I've done here. You would then basically set them up and do the cross product of that. Once you take product, then it says, give me the unit normal. And so you have to divide by the magnitude. And so you should have gotten an answer something like 2 times the 21 divided by 21. 1 times, minus 1 times square root of 21 divided by 21, and minus 4 times the square root of 21 divided. And if you crossed it the other direction, then this x would have been minus, and the y and z would have been. So we kind of. I think that hopefully to a little bit of an understanding of what he's like. And if you have any questions for you students, Friday at 8, or the remote students,
just one quick thing for you guys. If you guys have finished that last survey I sent out, thank you very much. I appreciate that. If you haven't, if you could finish it sometime this week, it'd be really great to remind your teammates.
You should do like a big video or something for people.
Yeah, Dr. Jensen?
Can't steal that idea, okay, guys?
Hey Larissa, can we have design reviews tomorrow?